Hello, students. Today, we are going to tackle one of the most important topics in organic chemistry and make it really, really simple for you. So let's start with a puzzle. You must have seen this in the lab, no? You mix two completely clear liquids, and suddenly, poof, a bright orange solid appears. I'm talking about the test with Brady's reagent, of course. It's quite dramatic, isn't it? Well, by the end of our session today, you will understand exactly why this happens.
Right, so today's topic is the core chemical reactions of aldehydes and ketones. And our focus is not on memorizing reactions. No, we are going to understand the one fundamental principle, the one single idea that controls how all these molecules react. Once you get that, you can predict any product with full confidence. So, are you ready? Let's begin.
Okay, first things first. Let's look closer at that surprising color change, that orange solid. Understanding this simple lab observation is actually our key to unlocking this whole topic. So, to understand that reaction, we need to ask, why do these reactions happen in the first place? Every molecule has a point of attack, a weak spot. So what is the weak spot for aldehydes and ketones? Okay, the entire secret beta is the polarity of the carbonyl group. You see, this oxygen atom is very, let's say, electron greedy. It's highly electronegative. So in that C double bond O, it pulls the shared electrons towards itself. What happens to the poor carbon atom? It becomes electron deficient, or what we write as delta plus. And that delta plus carbon, that is the weak spot. It's a target just waiting to be attacked. And this situation directly leads us to the main type of reaction here. This is the exam-safe definition you should know, nucleophilic addition. It's exactly what it sounds like. A nucleophile, which is something rich in electrons, attacks that electron-poor carbonyl carbon. The name itself tells you the story. So what is really happening at the molecular level? Just think of it like a simple two-step dance. Step 1, the nucleophile, rich with electrons, comes and attacks the delta-positive carbon. This attack is so strong it breaks the weaker bond of the double bond, that is the pi bond. The electrons from that broken bond jump onto the oxygen atom. Step 2. The oxygen now has a negative charge and is unstable, so it quickly grabs a proton, NH+, to become stable. That's it. Attack, then stabilize. This two-step mechanism is the absolute key to understanding this chapter. Please pay close attention. Now, I know mechanisms can seem complicated. So to make this idea stick in your mind forever, let's use a very, very simple analogy. Just imagine the reaction is like a magnet attracting iron filings. The carbonyl carbon, that's our magnet, and the nucleophile that's coming in to attack, that's our iron filing. Look at how perfectly this analogy maps to the real concept. The electron-poor carbon, or delta plus, is just like the positive pole of the magnet. The electron-rich nucleophile is like the iron filings, and the reaction, the nucleophilic addition itself, it's nothing but the filing sticking to the magnet. Positive attracts negative. It's that simple, isn't it? But why does this matter so much? Why are we spending time on this? Because this isn't just theory for your exam. This one single principle allows chemists to build very complex molecules in a very predictable way. This is absolutely essential for making medicines and drugs, where you cannot afford any mistakes. Okay, the analogy is good. But now let's build a proper mental picture of the actual reaction. We'll go step by step to see exactly how this attack happens. So, step 1. Here is our target, the polar carbonyl group. See the delta plus on the carbon? And here comes our attacker, the nucleophile, which we can show as nu minus. It has that extra pair of electrons ready to donate. And now for step 2, the attack itself. Watch closely. The nucleophile uses its lone pair to form a new bond with that delta-positive carbon. Now, carbon cannot have 5 bonds, right? So something has to give. The weaker pi bond breaks, and both of its electrons jump onto the oxygen atom. They have nowhere else to go. And the final step, step 3. The oxygen atom is now negatively charged and very unstable. So what does it do? It quickly finds a proton, an H+, from the solution and grabs it. This neutralizes the charge, and there you have it. The reaction is complete, and we have our final, stable product. All right, now that we understand the theory, the mechanism, let's connect it to the real world. We'll look at examples you'll see in the lab, and also clear up one very common point of confusion. Remember the puzzle we started with, the orange solid? Well, now we can solve it. That dramatic color change with Brady's reagent is a perfect real-life example of nucleophilic addition. The nitrogen atom in the reagent acts as the nucleophile. It attacks the carbonyl carbon of the aldehyde or ketone, in this case acetone. This is the classic laboratory test to identify these compounds. Now for a very important application in technology and industry, the Grignard reaction. In this reaction, a very powerful nucleophile, a Grignard reagent, attacks the carbonyl. The really special thing here is that the nucleophile is carbon-based. This means the reaction forms a new carbon-to-carbon bond. Think about that. This is how chemists build bigger, more complex carbon skeletons. It is a cornerstone method for making so many essential medicines. Okay, now for a very common point of confusion. Many students see a double bond and think of alkenes, but you must not make this mistake. The C=O bond is very different from a C=C bond. Why? Because C=O is polar. The carbon is delta positive, so it is attacked by nucleophiles, which are electron-rich. A C=C bond, on the other hand, is nonpolar. It is an area of high electron density, so it gets attacked by electrophiles, things which are electron-poor. They are complete opposites. And one last very important point for your exams. Remember this. Aldehydes are generally more reactive than ketones. Why? It's simple, really. The carbonyl carbon in an aldehyde is less crowded. It has one small hydrogen atom attached. But a ketone has two, usually larger, alkyl groups. These bulky groups get in the way and make it harder for the nucleophile to approach and attack the carbon. It's a simple case of steric hindrance. Okay, so let's summarize everything we've learned into 3 key takeaways. If you remember these 3 points, this whole topic will be very, very clear for you. First, the core idea. Electron-rich nucleophiles attack the electron-poor carbonyl carbon. Second, the mental image. Just remember the magnet analogy, positive attracts negative. And third, the application. Think of the Grignard reaction and how it helps build important molecules for medicines. So my advice to you is this. Don't try to memorize dozens of reactions. Instead, just focus on this framework. Remember the core idea, hold on to that mental picture of the magnet, and know one key example. If you do just that, I promise you, this topic will feel so much lighter and more logical when you face it in your exam. And I'll leave you with this final thought. Now that you understand the why behind the reaction, you hold the master key to this entire chapter. You don't need to learn every single reaction by heart anymore. You can now predict what will happen when any nucleophile meets a carbonyl group. That is the real power of understanding the fundamentals.